Another way we can combine propositions is through conditional statements. These are also called if-then statements. So when you have two propositions, P and Q, then a statement of the form if P, then Q is called a conditional proposition or an implication. Proposition P, the if P, the first part, is called the hypothesis. And proposition Q, then Q, is called the conclusion. It's the second part. And we're going to be able to set up a truth table for conditionals. Typically, in this introductory part of logic, for new folks in the world of logic, this table is something that gets memorized, though I am going to try to contextualize it with the fun and cheeky example. So we're going to let proposition P, our hypothesis, be if I shower or just I shower. And then proposition Q, the conclusion is going to be I smell good or then I smell good. So, if you're looking at if P, then Q, that would be if I shower, then I smell good, which, I think we can all agree is usually the case. So let's look at a truth table here. Let's suppose that you do shower. You've done it. You've taken a shower. And let's suppose that you now smell good. So if you were to say something like, if I shower, then I smell good, or I've showered and now I'm smelling good, it would follow that that would be true. But if you shower, but now you don't smell good, like that's weird. You should be smelling good after your shower. Really makes you wonder what's going on in there, huh? Okay, so this is not true. This is false. The implication is false. You cannot shower and then smell bad or not smell good. But we also got to consider when the proposition is false. So if the proposition is false, if I don't shower, you could smell good though. What if you don't shower and you smell good? Maybe you were still smelling fresh from a previous day's shower. Maybe you had a cologne. Maybe you're not a stinky person in general. Like this is okay, you could do this. And then lastly, what if you don't shower and you don't smell good? You may be here now. But certainly this is reasonable. This would be a true statement. You didn't shower and you don't smell good. So here's our truth table for conditional proposition. And some ways you can think about this is it's kind of like a promise that you're making. So if proposition P, your hypothesis, this is your promise. If I do this, then the smelling good is gonna follow. And so, of course, if you shower and then you smell good, like you've kept your promise, right? So that's true. But like if you shower and you don't smell good, you've not kept your promise. Like I was told that if I shower, I was going to smell good, and I don't. So that's why that one's false if you kind of think of it in terms of a promise. Similarly, with the proposition P, the hypothesis, with that one being false, like if I never showered, then it's not up to me what happens next because I haven't even fulfilled the first part. So these are actually called vacuously true. Whenever your proposition P, whenever your hypothesis is false, the implication is always true because you've never really started to begin with. And something to notice is actually that the conditional is true always, except when the proposition was true and the conclusion was false. It's always true unless you take a shower and you come out stinky. That's the only one that doesn't work. There's some alternative language for if P then Q. Some of it might pop up, some of it might be just for fun. P is sufficient for Q. So this one's pretty popular. Once you guys change your major to mathematics and join the dark side, you'll see that a lot. P implies Q. This one is very common. Q if P. I don't know. It feels like you're just being fancy for no reason. P will lead to Q. Q is necessary for P. Also kind of math majory there. Q whenever P, ooh, and I think those are the only ones that we have for alternative language for the conditional proposition. So I want to do some examples. We're going to decide if a conditional statement is true or false. And what we have on the bottom right of your screen is the generalized table. It's what we just did. You've got your, I took a shower, but now I'm stinky. Example right here, back in action, the arrow from P to Q in the header of the third column. This is very common notation, and it says, if you were to read it out loud, P implies Q. So P implies Q is the other very common way of saying if P then Q. And in notation, we write P, arrow, Q. Okay, so I've got this for reference. We're going to decide if a conditional statement is true or false. Here we go. If Rome is the capital of Houston, then we are all on the moon. And you might be thinking, this could not be more false. Everything about this statement is false. Like nothing here is true at all. But what might surprise you is if you look at this in the context of an implication statement, you've got your hypothesis and you've got your conclusion. So first, we're going to determine if the hypothesis is true or false. Then we're going to determine if the conclusion is true or false. And then we're going to reference our table and see where does that put us and what does that tell us about the implication's truth value. So hypothesis P is Rome is the capital of Houston. I think we can all agree that that's false. Conclusion Q is that we're all on the moon. That's also false. So I've got two false things here. And this corresponds with the last row of our truth table here. So remember that whenever the hypothesis is false, the whole thing is just true. It's called vacuously true. We never even really started. We never delivered on our promise of the hypothesis. So in terms of a conditional statement, the conditional statement is true. Even though everything about the statement is false, the implication is true. Like if I just vaporize right now, then you all turn into purple fairies. Also a true statement. All right, let's look at another one. If May is the 5th month, then 5 plus 3 equals negative 99. So we're going to break this down into hypothesis and conclusion. And you might be looking at this and you're like, well, May is the 5th month. But that last part, I don't think so. So here's our hypothesis P, May is the 5th month. And then our conclusion Q is 5 plus 3 equals negative 99. Hot tip, it does not. So the hypothesis is true. May is the 5th month of the year, and the conclusion is false. So let's look at where that puts us in our table. This is true, false. So this is, if I take a shower, then I'm stinky. So that's false. This conditional is false. One more example here. If x minus 2 equals 3 means x equals 5, then Austin is the capital of Texas. All right, here we go. Again, you want to break it into your hypothesis and your conclusion. So the hypothesis P is that x minus 2 equals 3 means that x equals 5. And if you were to solve x minus 2 equals 3, you would get that x equals 5. Austin is the capital of Texas. That's also true. So I have a true and a true. And I want to look at this in my table. Where do I have the hypothesis true and the conclusion is true? First row, if I take a shower, then I smell good. That's a fact. This conditional statement is true. Here's an example that's very similar. If x minus 2 equals 3 means x equals 0, then Houston is the capital of Texas. So here, hypothesis and conclusion are the equation bit and solution bit. That's a hypothesis. And then Houston being the capital of Texas, that's the conclusion. So certainly the conclusion is false. What about the hypothesis? If x minus 2 equals 3 means that x equals 0. Well, that's not right. Because if I were to plug in x equals 0, then I would get that negative 2 equals 3, and that is definitely not true. So hypothesis is false. The conclusion is also false. So this puts us in the fourth row. So the conditional statement here is true.